Today, I want to explain a piece of technology that quietly guides billions of journeys every single day around the world. That technology is the Global Positioning System, more commonly referred to by its short name, GPS. Most of you probably use GPS in some form whenever you ask your phone for driving directions. But almost nobody stops to consider the genuinely remarkable physics that determines your location in real time. The basic principle behind GPS is surprisingly simple, although the engineering required to make it work is enormous. Far above the Earth, roughly 20,000 kilometers up, a network of about 30 active satellites orbits our planet. These satellites are arranged in carefully spaced orbital planes, so that from any spot on Earth, several of them are always visible. Each satellite carries an extremely precise atomic clock, which keeps time accurate to within billionths of a second. Every satellite continuously broadcasts a radio signal, and embedded in that signal are two crucial pieces of information. One piece is the exact time the signal was transmitted, and the other is the satellite's current position in space. Your phone, or any other GPS receiver, picks up these signals using a small built-in antenna. The receiver then compares the time stamped on the signal with the time on its own internal clock. The difference between those two times tells the receiver how long the signal took to arrive from the satellite. Because radio waves travel at the speed of light, multiplying that travel time gives the distance to the satellite. So now your phone knows it sits somewhere on an imaginary sphere with that satellite at the center. Of course, a single sphere covers far too many possible locations to be useful, so we need more satellites. When the receiver gathers signals from a second satellite, the two spheres intersect along a circle. A third satellite narrows the result down to just two possible points, only one of which lies near Earth. This geometric technique of using overlapping distances to find a point is known as trilateration. However, a fourth satellite is also required, and this is where many people get confused about the system. Your phone's clock is nowhere near as accurate as a satellite's atomic clock, so its time is slightly wrong. The fourth satellite provides an extra measurement that lets the receiver mathematically solve for the clock error. Once that correction is applied, the receiver can pinpoint your latitude, longitude, and even altitude with impressive accuracy. There is one more subtle factor that engineers cannot ignore, and it involves Einstein's theory of relativity. Because the satellites move quickly and orbit in weaker gravity, their clocks tick at a slightly different rate. Without correcting for these tiny relativistic effects, GPS positions would drift by several kilometers each and every day. So whenever you tap a map app and a small blue dot appears, an extraordinary chain of events occurs. Atomic clocks, orbital mechanics, radio signals, and even relativity quietly work together to place you on the screen.